In this presentation, we will introduce two more important Six Sigma and Lean measures: cycle time and rolled throughput yield. Cycle time is a very important concept in Lean and Six Sigma, and it's often confused with processing time and lead time, but they're very different things. Process time is how much time it takes to actually perform all of the steps in a process. It does not include time when the product is waiting to be processed or is being transported or delayed for some reason. Process time is the time of the actual work. Cycle time is typically defined as the time required to complete one cycle of an operation. Cycle time is the time from the beginning to the end of a process, including waiting time and other delays. That is, it's the time it takes an individual product to travel from the beginning to the end of the process. Consider that process time for a product might be 2 minutes. However, any individual product may spend a significant amount of time waiting between steps in the process. How much time is greatly influenced by batch sizes and work-in-process inventory. The larger your batch sizes, the more work-in-process inventory you will have. For example, if you're processing batches of 100 pieces, typically you will be processing one piece through a process step while the other 99 wait. One way to test cycle time is to put an identifying mark on a part at the beginning of the process and see how long it takes to come out the other end of the process. It's not unusual for cycle time to be 10 to 20 times as much as process time. Lead time is the time between a customer order and the delivery of that order. It includes cycle time, but may also have delays after the order is placed and before the work begins. Often, in our improvement efforts, we can reduce cycle time. The most immediate benefit of reducing cycle time is to better serve our customers. These improvements are often related to the current state process maps that we discussed earlier. We can analyze these process maps and remove waste from the process. In the last module of this course, we will learn about what these wastes are and how to do that analysis. Reducing waste can mean, in part, reducing the wait time between operations and reducing batch sizes. If we can reduce wait times, cycle time will improve, and because product will spend less time waiting. If we can reduce batch size, we can reduce work-in-process inventory, which will also reduce cycle times. It's important to note that all of those things, waste elimination, work-in-process reduction, and cycle time, go together. They're part of a lean system. You can't pick and choose the parts that you like. Our next measure is called rolled throughput yield. Rolled throughput yield is the probability that a process with more than one step will produce an error or a defect-free unit. This also applies when multiple components are used to create a single product. Before we can calculate rolled throughput yield, we need to calculate first pass yield for each operation or each component. First pass yield is actually just the complement of our defects per unit calculation. Remember, to get defects per unit, we divided the number of defects by the number of units. Let's take an example. Say we're producing 50 units and we find 3 defects. We divided 3 by 50 and we get a DPU of 0.06. We can get the complement of our DPU calculation by subtracting it from 1. In this case, the answer is 0.94. We can interpret this to mean that we have 94% good quality. It also means that for any individual part, there is a 0.94 probability that it will be defect-free. This is our first pass yield. It's also possible to account for rework in this calculation, but for now we will keep it simple. Now let's add some more components to our assembly. We now have 4 components in our assembly. The first pass yield for these components is 0.94, 0.96, 0.98, and 0.96. Again, that is also the probability that a component will be defect-free. It would seem that these numbers do not look too bad, but we want to know how many of our assemblies will be defect-free. Our assembly could have a defect occurring from any one of these components. According to the multiplication rule of probability, we can find the probability of multiple events happening at the same time by multiplying the individual probabilities. So, if we multiply the first pass yield, or probability of good parts, for each component together, we can get the probability that the assembly will be defect-free. This is rolled throughput yield. The answer, rounded off, is 0.85. That is, there's only a 0.85 probability that these 4 components will produce a good assembly. Imagine how this works in complex products, like a computer or an automobile transmission. The more components or steps in the process, the more opportunities for failure. This time you try it. Remember, to get DPU, divide defects by units. To get first pass yield, subtract DPU from 1. First pass yield is the probability that a component will be defect-free. Now, multiply the first pass yields for each component together to get the rolled throughput yield for the assembly. Now pause this video and try the calculations. For each component, we divided the number of defects by the number of units to get the defects per unit. Then we subtracted that result from 1 to get the first pass yield. This is the probability that a component will be defect-free. Then we multiplied those probabilities together to get the rolled throughput yield, which was 0.95. So there is a 0.95 probability that an assembly made up of these components will be defect-free. Did you get it right? If not, review the video and try again.